nanoHUB.org.
Online simulation and more for nanotechnology.
Hello, everyone, and welcome to the nanoHUB webinar, Density Functional Theory, Introduction and Application. We're very excited to have you all here today joining us. Our presenter, Dr. André Schleife, is a Blue Waters Associate Professor in Material Science and Engineering at the University of Illinois at Urbana-Champaign. He is an editor for a journal and actively organizes national and international schools, workshops, and tutorials to advance the community around cutting-edge first principle simulations of materials. So thank you, Dr. Schleife, for being here with us today. We're very excited to be presenting this webinar.
Thank you so much for the introduction, and thanks to nanoHUB for this opportunity to talk about DFT. It's of course not a technique I invented, but it's a technique we use very heavily in my group, and we also teach in class. And so talking a little bit about it and making it accessible to a larger community is great. So thanks nanoHUB for that. Thanks also to various funding sources that you can see at the bottom of the slide for supporting our research work. Now, what I want to start with is of maybe these little 3 vignettes of research that we do in my group. So we work typically with excited electronic states. So we simulate electronic excitations using quantum mechanical first principles techniques. And the goal of these simulations is usually related to electronic, optoelectronic, and maybe even spintronic materials. So we aim to develop and understand materials that can be used for faster and maybe smaller and more efficient electronics. So that's sort of in this first category. More recently, we started looking into materials that can be used for quantum information. So this is again just a cartoon picture here. But what we're interested in there is to understand how to manipulate defects in a material. So we run again first principle simulations to understand how to maybe change the concentration or the type of defects that's prevalent in a material. And last but not least, we're also interested in materials for extreme conditions. So in this case, you see a picture here from a simulation of proton irradiated magnesium oxide. Now, a little bit about myself. So I want to just point out 2 things, maybe my hobbies. So if I have free time, 2 things that I really like to do is to go to concerts, maybe rock or metal concerts. You can see 2 pictures of that here. One with Professor Kim C. She's at Caltech investigating battery materials. She was a postdoc here. We know each other really well. We went to a concert. This is before the pandemic. And then here, maybe some of you guys know Professor Patrick Rinke, who is in Helsinki. So this picture is from this summer when we went to the Tuska Festival. Anyway, when I'm not on travel, when I'm local, I like to fly small airplanes. So that's a hobby I started during the pandemic. So you can see here at the Champaign airport, and it's kind of fun to look at, beautiful Illinois from above, even maybe the Midwest all the way to Indiana and Purdue included. Okay, so the goal for today, I divided this into 3 points. I want to start, given the diverse audience, I want to start by motivating what we're doing. So maybe telling a little bit about the background and why are we ending up using DFT. That will be the first part. In the second part, I will talk a little bit about what are the underlying assumptions or equations of DFT. So I call that formulation and implementation of DFT. And then in the remaining third, we'll talk about applications. So I'll show you how to run DFT, specifically how you can run it on nanoHUB, both for research, maybe more importantly for teaching, right? So research groups may want to install DFT software locally, but for teaching, we have had very good experience to use nanoHUB. And I'll show you a couple of those examples. I put 2 here on the slide, which is the total energy and bulk modulus, as well as the band structure. And what you see at the bottom of the slide, on the second half, is actually an electron density, right? So the density we're talking about in density functional theory is, of course, the electron density. And what you see in this figure is the electron density of graphene. So that's from one of our simulations. Okay, so before we dive into the nitty-gritty details, we'll start with a bird's eye view of the situation. And I usually like to show this slide that tells you a little bit about computational material science in general. So if you are performing, or if you want to perform, computer simulations to do your research in material science, you have, of course, a vast number of techniques and software available at your disposal, right? And we're not going to talk about all of them, but what applies to all of them is that the cost that you put into a given simulation depends on the level of accuracy that you want to get within that given technique. So that's true for essentially all of the approaches that you can see on the slide. That being said, depending on your goal, and I think that's maybe one thing that you should know up front, depending on your goal, you have to sort of think about what is the right length and time scale that you want to simulate at. And that's a decision you have to make, right? So depending on the scientific question that you want to answer with your simulations, you have to pick sort of like that length and time scale, and then that dictates maybe a method that you can use or a set of methods, and then from there you would pick a code or a simulation package. Density functional theory that we're talking about today is at this length scale and time scale, right? So maybe short time scales, femtoseconds, electronic time scales essentially, as well as atomic or electronic length scales. Okay, now now that we settled that, I would say that we're at the microscopic level, meaning at the level of individual atoms and electrons. You probably don't have a hard time believing me that for that we have to use quantum mechanics. Okay, so the normal approach that describes materials at the microscopic length scale is quantum mechanics. And the model that we have of materials is sort of like summarized in a few bullet points here. So materials consist of atoms, of course, and then atoms in turn consist of nuclei that have protons and neutrons in them. Those we usually we approximate as point charges. So we're not really dealing with protons and neutrons specifically. And then those positive charges are surrounded by tightly bound core electrons, maybe at very short distances. And then the further out you get, there are still electrons. And at some point, those turn into valence electrons. Those are the ones that determine the chemistry of a material. Okay, so that's sort of like the model that we want to describe. And you probably also believe me that for that model, either for individual atoms or for molecules or for solids, what we have to do is we have to solve the laws of quantum mechanics. We want to do that for actual materials, not just for atoms, right? We want to do that for molecules, maybe for solids, for surfaces, and very complicated systems. And the reason we want to do that is that we want to obtain properties that we can compare to experiment, right? So that are directly comparable to experiment. We want to perform predictive simulations that produce numbers that we compare to measurements that people perform in their labs. Examples of such properties include the bonding and the structure of the material. I mentioned that already. It can also include electronic, magnetic, and optical properties of your material. And it can go all the way to chemistry and reactions. So all of these things involve either ground or excited state properties of electrons, and that's something we would like to solve. All right, so that's the starting point. Now, that starting point is known, I would say, since the 1920s. What I put here is a quote from Paul Dirac. And what Paul Dirac said directly is that the general theory of quantum mechanics is now almost complete. Again, he said this in 1929. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are completely known. All right, now here's the suspense, because he finishes the sentence by saying the difficulty is only that the exact application of these laws leads to equations that are much too complicated to be soluble. So that's the suspense. In other words, we know the laws, we know the equations, but we can solve them. So Paul Dirac said this in 1929, and that is still true today, as I will illustrate in just a moment. Before I do that, I will tell you how we go about quantum mechanics. So usually I like to, when I teach on quantum mechanics, I like to give this sort of like three-step procedure, right? If you're facing a problem that you want to solve in quantum mechanics, you have to do three things. Step number one is you have to write down your Hamilton operator. Okay, so that I will write down here in a moment. So step number one, write down the Hamilton operator. That's usually an easy step because this is where you come in as the person developing a model, right? So you can decide what physics to include. You can decide what potentials to include. You determine what it is that you want to simulate. That goes into your Hamilton operator or Hamiltonian. And that Hamiltonian looks like this. It's the sum of the kinetic and the potential energy. And again, you determine what goes specifically into the potential energy. This step is easy because you decide. I'll show you the specific example for materials in a moment. Step number two is you want to solve the Schrödinger equation for this Hamiltonian. So I write down the time-independent Schrödinger equation here, which applies this Hamiltonian to a wave function. Right, so we can insert the Hamiltonian if you want to, which would lead to kinetic plus potential energy applied to the wave function. And that's equal to the total energy times the wave function. So that's the time-independent Schrödinger equation. This step is hard. It's hard for various reasons. One reason I'll illustrate on the next slide, just to give you an idea how hard it is. It's exponentially hard. But if you are able to solve this Schrödinger equation, in other words, if you are able to complete this step number two, you can then move on to step number three, which is you use this solution, and solution meaning in this case total energies and wave functions, to compute observables. So what do I mean by observables? These are quantities that you can measure in experiment. So one example I picked here for this talk, because we're talking about density functional theory, is the electron density. And I'll write down the expression for that as well. So if you want to compute the electron density at position R, or the probability of finding an electron at position R, what you do is you sum over all your orbitals. You have an occupation factor that tells you whether the orbital is occupied or not. And then you add here the square of the wave function. Okay, so that's our electron density. That step, again, is usually easy once you have the wave function. Again, the tricky part is to get the wave function. But once you have it, you can integrate over it and things like that. So that's step number 3, again, I would say is more or less easy. What I illustrate here is this electron density, just so that you have some idea what this looks like as a picture. Okay, now, why is it difficult to do step number 2? So the example that I show here, and this actually I think is very, it's kind of instructive because it really illustrates this exponential challenge. The example I pick here is an iron atom. Okay, so we take one atom of iron, only one. Iron itself as a bulk material looks like this. I just put this here for illustration. This single iron atom has 26 electrons. And that means that our wave function describing that iron atom will have a total of 3 times 26, which equals 78 variables. So why is that? Well, our wave function would look like this, right? We have the wave function of that depends on the first electron, all the other electrons, all the way to 26. And each of these positions that I put here is, of course, a position in 3 dimensions, so it's 3 variables. So you have 78 variables. All right, so far so good. Now what you say, okay, you can come along and say, okay, I'm going to solve this on a computer, so I want to store my wave function on a grid. That's fine. And then we pick, for this example here, just a discretization of 10 points along each direction. So each of these 78 variables is discretized by 10 points. The problem comes now. This leads to a total of 10 to the 78 numbers that you would have to store for the wave function of one iron atom. That's a large number. And just to illustrate how large it is, I compare it to numbers that you're familiar with. So let's say you take a single precision on a computer to store your numbers. Each of those 10 to the 78 numbers, that means 4 bytes per number. So in other words, you need 4 times 10 to the 78 bytes. Still a large number. But to put it in perspective, I compare it in here on this slide to all the data stored worldwide in 2020. So by the way, that's a number I Googled. Please don't quote me on that. But what I found on the internet is that this was 64 zettabytes, which is 64 times 10 to the 21 bytes. So many orders of magnitude lie between those two numbers. And so that illustrates that even just storing the wave function is extremely challenging. Specifically, it's exponentially challenging. All right. So what that tells us is that we have to not do that and instead look at approximations. And what I'll do now is I'll tell you essentially step number 1 for real materials, like we want to write down our Hamiltonian, and then I'll talk about how to solve it if we're involving approximations. All right, so here we go. The Hamiltonian itself, let's say we make one more approximation here, which is the Born-Oppenheimer approximation, which says that we fix all the ions of this material in their positions. So that could look like this. I put a cartoon picture here for titanium oxide with sulfur doping, right? In this case, there's one sulfur atom here, the green atom you can see. So let's say we fix the ions in those positions. And now we're interested in solving the Hamiltonian of the electrons for this material with those ions fixed at those positions. Okay, so what does this Hamiltonian look like? So I put the equation here. The Hamiltonian has 3 terms. One is the kinetic energy of the electrons. So this is the kinetic energy. The second term is the interaction between the electrons. This is this one. This is the electron-electron interaction. And the last term is the electron-ion interaction. So that's the external potential that the electrons feel, which is imposed by the ions. The ions are positively charged, the electrons are negatively charged. So both of these interaction potentials here are Coulomb interactions. So I've just write electron-ion here. That's the Hamiltonian. So when I said earlier, step number 1 is easy. That's it, right? That's step number 1. We have the Hamiltonian. That's the Hamiltonian we want to solve. People, again, realized this, of course, very early on. Step number 2 is solving the equation, Schrödinger equation, and that's difficult. And so what people did historically, they developed approximations, right? So they developed approximate versions of this equation that includes things like the Hartree approximation, Hartree-Fock, and many others. I'm not trying to be exhaustive here. I just want to mention those for historical purposes. There are more than one way of approximating and more than one way of trying to solve this. DFT is only one of them. But what is general is this point here. And any of these methods that you pick, they have varying degrees of approximation, which constitutes a trade-off in terms of accuracy. And along with that, they are differently fast, right? So more approximate methods are usually faster, less approximate methods are usually slower. So in other words, you have to balance this trade-off between accuracy and speed, no matter what methods you use. Exact solution is impossible. All right, and in that spectrum, DFT is at a, I don't know if I would say a sweet spot, but certainly at a favorable spot, because it balances well between cost and accuracy, I would say. I think that is the main reason it's so widespread nowadays. So it's not exact, at least not once we apply it in practice. And at the same time, it's very widespread because we can carry it out for real materials. All right, so at this point, we'll say, okay, we have the Hamiltonian, we want to compute things for real materials. Step number 2 will be done by DFT. That's sort of like the stage for DFT. Okay, so now let's go to DFT. And what I promised that I will start with the sort of like the very basics. So I'll tell you a bit about the theory first, and then we look at the implementation and how we can run it. So one of the that was not just one milestone, but one milestone that happened was that Walter Cohn proved in the 1950s, 1960s, so the paper was 1960, but that's when he proved that the ground state energy of the electronic system can be written as a function of the electron density, of the ground state electron density instead of the wave function. So in other words, what you have on the left-hand side here is the wave function. What you have as a cartoon picture anyway. What you have on the right-hand side is the electron density. And what Walter Cohn proved is that the ground state energy of this electronic system can be written as a function of the electron density instead of the ground state wave function. So the simplification comes in here. Instead of having a function of 3 n variables, like 78 variables for one iron atom, we now have a function of 3 variables. It's the electron density as a function of position. That is, even without looking at any math, this is a tremendous simplification, and you probably believe that this makes these simulations, or makes the method implementable in simulations. Okay, so now let's look a bit more at the mathematical details, not too much, but briefly. And what happened is there were 2 Hohenberg-Cohn theorems that laid the foundation of DFT. The first one is, so it's called the first Hohenberg-Cohn theorem. What that says is that the external potential is a unique function of the density. Okay, so to illustrate that point, I have written down here first this procedure. This procedure is how you would get the electron density if you were able to solve the exact Schrödinger equation. Okay, so typically you come along, you write down your Hamiltonian in step number 1. You write down the Schrödinger equation, you solve it. Again, we know now that it's not so easy, but let's assume that it was so easy. You solve it, you get all the eigenstates of the Hamiltonian. Then you can look at the ground state of that Hamiltonian. Once you have all the eigenstates, you just pick the ground state. And from that, you can compute the electron density. So that is how you would do, how we compute the quantum mechanical electron density. What the first Hohenberg-Cohn theorem says is that this density connects back to this potential. So in other words, the external potential is a unique functional of the density. And what that tells you is that once you have the density, you know what the potential was. So that's the first Hohenberg-Cohn theorem. That shows that we can use the electron density as a basis variable instead of the wave function. So that's a tremendous, I would say, theoretical advance, but it does not tell you yet how to do it. And for that, we need a couple more steps. The second step that we need is the second Hohenberg-Cohn theorem, which uses this fact that the electron density is can be used as a variable and applies it to one quantity of interest. So in other words, the second Hohenberg-Cohn theorem tells you how to make use of the first Hohenberg-Cohn theorem by computing a quantity of interest now as a function of the electron density, not of the wave function anymore. And what the second Hohenberg-Cohn theorem does that for is the total energy as the sum of kinetic, external, and electron-electron interaction. And what the second Hohenberg-Cohn theorem says is that the density that minimizes this total energy is indeed the exact ground state density. So in other words, now you have not only shown that the ground state density is a perfectly fine variable, now you also have a recipe of how to get this ground state density, which is a variational principle, meaning you can find the minimum of this energy, and once you found it, the density that gave you that minimum is indeed the exact ground state density. All right, that's the foundation of DFT. The question is, do you guys think we made an approximation yet? All the way up to the second Hohenberg-Cohn theorem. And I'm not talking about Born-Oppenheimer approximation, by the way. Have we made an approximation of the electronic Hamiltonian? Yes, no, or I'm not sure. So about a third said yes, 2/3 said no, and maybe 20% said I'm not sure. So number B is correct. We have not made an approximation yet. So DFT up until here is in principle exact. There will be a caveat, of course, right? But I haven't told you yet what the caveat is. All right. So now, in order to actually find this solution in practice, what we now have, what people then developed, and this was Cohn and Sham developed that approach. They said, okay, what we're going to do is we know how to compute the kinetic energy of non-interacting electrons. And so if we can map our many-body system, our interacting many-body system, to a system of non-interacting electrons, which is then nowadays called the Cohn-Sham system, if we can establish that mapping, then we have, and we put a constraint on that mapping, which is that the ground state electron density of the interacting and the non-interacting system have to be identical. So we want a mapping that maps both systems while making sure that the ground state electron density is identical of both systems. All right, if we can establish that mapping, all we now have to do is solve that non-interacting system, the Cohn-Sham system, find the ground state density, and then we have the ground state density of the interacting system. Okay, so that's the mapping they established. Now, what it gives us is, I'll show you the equation. I don't want to write those because it may take me too long and you may not be able to read everything I write. So what they then developed is the Hamiltonian for the non-interacting system. So they do two things. Just as I hinted at here, they replace the kinetic energy of interacting electrons by the kinetic energy of non-interacting electrons. So that's number one. They also say, well, once we're making approximations, or we will make approximations down the road, we can also replace the full electron-electron interaction by a Hartree potential. We know that's not correct, but at least it captures a certain fraction of what electrons do when they interact. Okay, so that gives us the kinetic energy of non-interacting electrons, gives us a Hartree interaction. Of course, we need an external potential. These are our ions, right? Those are still present. We need those. And now we made an error because we made these two replacements, right? We replaced the kinetic energy and the electron-electron interaction. We make up for this error by introducing a functional that's called the exchange correlation functional. That's the Cohn-Sham approach. So this gives us a single particle Hamiltonian that you can solve for single particle orbitals that is established, or that's written down such that the ground state of its Hamiltonian gives an electron density that's identical to the electron density of the complicated interacting many-body system. At this point, do you think we made an approximation? At this point that you see here, this equation here, did we make an approximation? Same answers as before. Number one is yes, we made one. Number two, no, we didn't. And number three, I'm not sure.
Yeah, well, people are answering that. We did have one question come in. Someone asked, why was there an inequality on the RHS of the second Hohenberg-Kohn theorem?
Of the second right-hand side, yes. Well, I guess it's equal if you are at the ground state density, and it's not equal if you're not at the ground state density. I think that is probably the answer. Right, so any non-ground state density, if you plug it into your total energy, you get a number, but that's larger than the ground state total energy. And once let's say you try 500,000 different electron densities, and one of them is the ground state density. Once you hit the ground state density, this becomes an equal sign. I think is that what the question goes to?
Oh, yep, they said that answered it.
All right, so now the results flipped. We have, I guess, higher participation, which is good, but we also have maybe about half of the people say, yes, we made an approximation. 12% said no, and only 5% are not sure. Okay, so now we flipped the correct answer. We still have not made an approximation. This mapping to the Cohn-Sham system is exact in principle. The problem is, and that's maybe, I hope I didn't trick you. The problem is we don't know what the exact exchange correlation functional is. If we know the exact exchange correlation functional, we will find the exact ground state density with this approach. In practice, of course, we don't know what this functional looks like. So the approximation, so in case some of the yes answers here were going for the fact that the exchange correlation functional will be approximated, that's correct. But the way these equations are written right now, there's no approximation yet. That'll come next. Okay, very good. So let's do so a quick recap. I think I told you we have the kinetic energy of non-interacting electrons here. We have the Hartree energy and the external potential. And I will just write down real quick what I said earlier in words, which is that this VXC is making up for the two approximations, sort of like the two replacements we made. We didn't make an approximation because VXC makes up for it, but we replaced the exact kinetic energy with the non-interacting kinetic energy, and Vxc has to make up for that difference. And we replaced the exact electron-electron interaction with the Hartree interaction. And Vxc needs to make up for the difference. So if we were able to develop a Vxc that does this exactly, we would be completely fine. Everything would be exact. Of course, the way I say all these things, you can already guess where this is going. The exact form is not known, and we don't know how to do this exactly. And this is really where the approximation comes in when you do DFT. All right, so we have to approximate the exchange correlation potential. In some sense, since we don't know the exact form, these approximations are sometimes it's not absolutely clear up front how accurate those are, right? Those are somewhat uncontrolled approximations. I'll list just a couple of examples here that are used in practice. So already in the early days, the local density approximation was used, right? So this is an approximation that computes this exchange correlation contribution for a free electron gas that has the same density as the actual system we want to describe at point R in space. Was in the early paper already, right? Very early on, and it's still used today. And then people developed all sort of other approximations that are increasingly more accurate and that are suitable for certain systems. So I list a couple of here, right? Generalized gradient approximation, still very much used nowadays. And then you can correct for certain deficiencies, right? So for instance, self-interaction can be corrected by incorporating it into the functional. People can use the Hubbard model to improve the functional. Hybrid functions are very common nowadays, especially if you're looking at electronic properties. Exact exchange is one. Van der Waals interaction is a tricky point that you may want to incorporate specifically. And nowadays there are research efforts that try to develop functionals by using machine learning. So in other words, exchange and correlation is the crucial approximation, and that's where you have to be careful when you do DFT. So the accuracy, I say this here, depends also not just on the approximation, but also what material you're applying that approximation to. Great. So at this point, I think we made our way through the foundation of DFT. This is what your DFT code will solve. And in the remaining, I would say, maybe 25 minutes or 20 minutes plus questions, what I'll do is I'll show you some examples of using DFT and specifically of running on nanoHUB. And so what essentially I'm coming to the last point in this three-step procedure here. And so I'll start by mentioning some applications. So I did a little bit of that in the beginning, but one big application of DFT is to predict atomic geometries and crystal structures. So crystal structures, I put this picture of Bravais lattices as an illustration. So you can simulate electronic properties for all sort of different crystal structures of a material, and by looking at the total energy, you'll find which is the crystal structure the material wants to be in at equilibrium. And one example, which is from this paper here, is for instance the crystal structure of silicon as it changes if you compress the material or if you decompress the material. So as you go along, these pressure values that are listed here, the structure the material wants to be in changes, and DFT predicts this very accurately. So oftentimes lattice parameters, for instance, are within a few % of experiment if you predict them with DFT. You can also perform molecular dynamic simulations with this framework. You can compute forces from your electron density, and by using these are the Hellman-Feynman forces, and by using those forces you can perform molecular dynamic simulations. You can look at vibrational properties, you can look at defect geometries. So the applications of DFTs are vast, and I'm not trying to be exhaustive. I'll point you to some books at the end that may capture this topic a bit more in detail. What I want to do now in the remainder is I want to show you how this leads to software that can be run. And specifically, I'm picking here one package, not to advertise it or anything. I just pick it here because that's the package that nanoHUB runs. That code is called Quantum Espresso. And what Quantum Espresso is an integrated suite of open source codes that perform electronic structure calculations. Okay, so it has a bunch of code implemented. It has plugins for advanced tasks and various third-party packages. So it's a very comprehensive software package that is developed by many people around the world nowadays, right? It's open source and people can develop it. But why it's important for this presentation is it can be run on nanoHUB. I'll open this link here in just a moment. This link is the one that will get us there. And the reason that's important is, I would say, for two reasons. One is if you want to try out the method and you don't want to install a DFT code on your local machines, or maybe you don't have a machine ready to go, nanoHUB allows you to run DFT simulation on their website and explore whether DFT is maybe the right thing for the question that you would like to answer. So you can try it out, in other words. The other reason, and that's what we've used it very successfully for, these are the examples you'll see in a moment, is for teaching. So if you want to bring this tool to the classroom and you want to avoid students having to edit input files using the terminal and running on Linux machines, which can, students who are familiar with that will have no problem. But if you have a big class and everyone has to do that, and some of the people may not be familiar with the command line and things like that, having a web interface is a very, appealing way of doing these kind of simulations. Okay. The technical detail that I want to point out, because this will be our first exercise, is when you implement DFT, you have to make certain choices. In particular, the choices that you have to make is you have to decide how you represent your Quantum states, right? The eigenstates of the Quantum equations I just showed you a moment ago, how you represent those in a computer. There are various different choices, one of which is called a plane wave expansion. So that expands these wave functions into plane waves, and the plane wave coefficients is what's stored. That is the choice that Quantum Espresso makes. So Quantum Espresso is a plane wave DFT code, and this will have one implication for when you run it. You have to test that your basis set of these Quantum states is converged. I will demonstrate that in a second, how you would go about that. And then the other thing is it also uses pseudo potentials. This is again a choice that you have to make. You can either decide to describe all the electrons in your simulation or just the valence electrons. If you do the latter, you usually would be using a pseudo potential. Quantum Espresso does exactly that. To describe the electron-ion interaction, it uses pseudo potentials. And the first exercise that I want to do with you guys, or I will rather demonstrate it, because the audience is so large, I probably will not have the opportunity to look at your results. But what I'll do is I'll demonstrate how you compute the total energy in DFT and what convergence parameters to pay attention to. So this is usually what you have to do first when you start simulating a new material, either for research or for teaching. You have to check that your plane wave basis set is converged, and Quantum Espresso operates in reciprocal space. So you also have to check that the reciprocal space grid that you use to sample your Brion zone, that grid is also converged. So I'll tell you in a moment what I mean by converged. Hide this here. And so what I opened is simply this link to the nanoHUB tool. So if you open that link, I believe you should see this window. So what you see here is a graphical user interface to this DFT code, and you can put a certain number of parameters here. You can say, I want to run silicon in the diamond structure. So that's what we're going to do in this tutorial. We're not going to change the material. So we say it's the FCC structure. You can give the run a title. You have to provide the structure of the material, meaning the atomic basis in your primitive unit cell, and then you specify a lattice parameter. Okay, so this is the first thing that you have to specify. I'll leave it at the default values for now. The second thing that you have to do is, I mentioned plane wave convergence, or convergence of your plane wave basis. That is in the second tab here under energy expression. You have an entry here that is called wave function kinetic energy cutoff. Okay, so the plane wave basis works in a way that as you increase your number of plane waves, one way to do that is you look at the kinetic energy of the highest plane wave that you include, and all the ones with lower kinetic energy are also included in your expansion. And that sets one parameter that determines how complete your basis set is. By increasing your cutoff, you include more functions. By decreasing it, you include fewer functions. So this is your convergence parameter. And by convergence, I mean you have to test whether a result of your simulation, we're going to use the total energy for that, still depends on the choice of kinetic energy cutoff that you made. Because what you want is that it does not depend on this kinetic energy cutoff anymore. So how do you do that in practice? Okay, so for that, let me go back to the slides again. I'll show you the plot, and then I'll tell you how we get to this plot. So in practice, what you do is you make plots like the ones up here that plot the total energy as a function of cutoff energy. I write Rydberg here, and I'll tell you in a moment how I know that. So what you do is you perform a series of DFT simulations that produce total energies, one total energy per simulation. And in that series of simulations, you change the cutoff parameter. So let's try that. So I will demonstrate this for the system that we have here. And what I'll do in parallel is I'll plot my results. So for plotting, I just use Google Colab notebook here, super simple. I just import matplotlib, No fancy details, not even access labels. I'm sorry, we can include those easily in Matplotlib, but I didn't do it here. And then I just simulate for different plane wave cutoff energies in Rydberg. So that's what you specify here. And then I'll put the simulation results here into a second array, which I use as my y-axis for the plot. Okay, so I will not go through all of these simulations again. I'll just hit simulate here once, which you guys all can try out. Click simulate. In my case, it's super fast because these simulations are cached, so it just uses results I produced this morning. But once you have these results, you have all sort of different ways to analyze them. I will look at the raw output for now, because this is something that you want to do if you want to learn DFT. It's a good idea to look at the total output file. And what we're looking for is we want to look for the total energy that comes out of the simulation. All right, so I scroll down here. And the way Quantum Espresso does it, it puts an exclamation point at the total energy, which is the final result. So for our 16 electron volt cutoff energy, the total energy is minus 15 and all these other digits Rydberg. And that is what I put here. So I type this number and just type it over here as the number that matches with 16 Rydberg cutoff energy. And then you do that for more data points. I already this morning did it for 10 and 11 Rydberg plane wave cutoff. So, you just go back here to input. We put a different number here. I'll choose a new one now just for the sake of trying this. Let's do maybe, I don't know, 13. In the morning, I chose 10 and 11 and put the total energies here, but we just chose 13 now. I want to see if it actually runs a simulation. Let's see. We hit simulate. This one will now run much slower because I haven't actually prepared it before. Actually, it was not that much slower. All right, and then I go down back to the total energy here, wherever the exclamation point is. I think I scrolled past it, sorry. We go up a little bit. Here it is. Okay, so I can put my 13 here. I hope this works. I'm always a bit reluctant with live demos because usually something doesn't work and then the message gets lost. But anyway, I'll just type it here. So we put the total energy, same number. I put this number over here in my Google notebook, in my Jupyter notebook. So 946,545. Okay, 6545. All right. And then once you do that for a couple of data points, you do your plot. Of course. See, that's what I mean with live demos. Okay, there's a negative missing here. Sorry, hold on. Let me close this poll. What's the actual error? Okay. Oh yeah, I never got a comma here, of course. Awesome. So there you go, live demos. All right, let's try again. We just plot this. I don't know why it takes so long. Anyway, what it now does is it just plots this data. Yeah, sorry, for some reason this takes apparently forever to plot. Okay. All right, so and what you now see here in this figure is that the total energy in this case decreases, and you can also see on what scale it decreases. So what you want to do is you want to increase this cutoff energy enough that the result is not changing within a certain level of accuracy. And that gives you plots like the one that I showed you here in the slides, right? This is the one I created this morning. You can continue this until your result really becomes very steady and independent of your plane wave cutoff. That's the first test you need to do. If you don't do that, you are not sure if your result is actually accurate. The second test you need to do, and I'll show you that also in nanoHUB in just a moment, we plot the same quantity, which is our total energy, and this time we plot it as a function of the number of K points. So what you do with K points is you sample your Brion zone. Let me hide this and go back to input. And that is up here. So you sample your three-dimensional Brion zone with a certain number of points. So the default for silicon is 8 times 8 times 8 points. So that means 8 in X, 8 in Y, and 8 in Z direction. But this is also a number that you need to test that it's accurate enough. The idea is exactly the same. You run various total energy calculations, changing these numbers here. And this morning, what I tried is I used 6 times 6 times 6, 8 times 8 times 8, and 10 times 10 times 10. Okay? The idea is the same. You have to choose a set of numbers to try. Then you plot the total energy as a function of those numbers. And once you've done that, you will see whether this number converges or not. So again, careful here with the Y scaling. So we have this funny notation here. So you can see actually in this case, the dependence of the total energy is much less than for the plane wave cutoff in this K-point regime that I tested here. So in this case, I just used 3 data points. You'll make a plot until this plot becomes sort of flat. or I should say flat within a level of acceptable accuracy. The other thing that I want to show real quick is, in principle, one thing you will notice, let me actually hide this one more time. One thing you will notice, if you look at your output, just simulate, if you look at your output, and let's say we use an abbreviated view here, which is maybe energy versus SCF iterations. So you can see this plot has a couple of data points, right? There's one data point here, one data point here, one data point here, and one data point here. And between the last two data points, there's almost no difference anymore. So what do these SCF iterations mean? So SCF iterations are iterations of this loop here. So when you do density functional theory, the way it works is at the very beginning of your simulation, we don't know what the electron density is, so we have to guess it. And the code comes up with a guess. You have different choices for how to guess. One brute force way would be randomize your electron density. That's not a great guess because it is very far from the real electron density. You can also use a superposition of atomic densities, things like that. But you come up with the initial guess. You put that into your Hamiltonian to get the potential that corresponds to this electron density. Then you solve the Kohn-Sham equations. You compute a new electron density from those Kohn-Sham orbitals. And at this point, you decide, is the new electron density close to or identical to the previous one or not? If it's not, you go back into this loop and you do the same procedure again and again. This is called an SCF cycle, which stands for self-consistent field. So you do this cycle a couple of times until you are converged, which means your electron density or your total energy doesn't change much anymore. And at this point, you're done and the simulation is over. So if you see that in nanoHUB, that is what that means. Okay. Now, at this point, I want to move on to the example number 2, which is the bulk modulus. So in addition to, what we did right now was static total energy calculations, and we varied 2 numerical parameters, right? Those are not physical parameters in the sense that we're not trying to find a plane wave cutoff that matches any experiment or something like that, right? These are purely numerical parameters that we have to converge, meaning we have to make sure we choose these values in the simulation such that our result doesn't depend on the choice anymore. Okay. Alternatively, you can now do physics with this approach, right? So you can do material science if you want. So in this case, I used the example of a bulk modulus. We also use that in one of our electronic structure classes. And so just for background, what happens is at constant temperature, the bulk modulus relates the change in volume of your material with the change in pressure. So that's the definition that you'll find in your thermodynamics book. And if you decrease your volume, that corresponds to positive external pressure on the material. If you increase your simulation volume, that corresponds to negative external pressure. And pressure and energy are related with this relation. If you plug these 2 equations together, again, you've most likely done this before, but I want to walk through the steps just in case you've never seen this. What you end up with is an equation for the bulk modulus of your material, in this case of silicon, in a moment, that relates the curvature of your total energy versus volume curve, right? So this is E as a function of volume, total energy as a function of volume of your simulation cell. The curvature of that plot can be used to compute the bulk modulus. I will not go through all of the steps, but what I will show you is at least how to produce such an energy versus volume curve. And the way to do this is usually we start from the the equilibrium volume of your material, meaning the material under no pressure. You have to either know or determine that up front. In this case, we're going to use the nanoHUB provided value of 5.43 angstrom. And then we will change our volume in a certain range around that equilibrium volume. Not too large of a range. I put like 90% and 90%, so 10% to the negative side and 10% to the positive side here. You can use 5% or something like that. Don't go much further than 10%. In any case, you change your volume around this minimum and you compute the total energy as you change the volume. Let me show you what that looks like. So what I do here is I go back to my input. I go back to, you can reset your values here. I don't know, we can use, I put 16 here. Normally you would now put whatever cutoff energy you determine to be sufficient so that you're happy with the accuracy. I'll just put 16 here. And the same is true for the K-point grid. You put whatever K-point grid you determined to be converged. And then you go back to the input geometry tab. And here you can change your lattice parameter. So this is the lattice parameter of your cubic FCC silicon structure. And what I did here is I changed it, say, in steps of 0.003. So for instance, I can use 5.40 instead. Then I hit simulate, because now I want to change my volume. In this case, I made it smaller. All right, so I hit simulate, like this. Again, my run is fast because it's cached. And then I look at my output log. And now what I do is I need two quantities. I want to make an energy versus volume plot. So I will need again the total energy. So that's down here where the exclamation point is. Okay, here, oops, sorry, here it is. So this would be the total energy of this run. And you put that into the array for that data point, right? You put that on the right-hand side array for that data point. And at the same time, you want the volume, right? You want to plot an energy versus volume curve. So you need the volume of your simulation cell. You have two options. Either you compute it by taking the lattice parameter, and you know what, the vector, the primitive unit cell vectors are of silicon, and you compute the volume. At the same time, Quantum Espresso, or nanoHUB in this case, also outputs the volume of the simulation cell that you provided. So this is in the output, and it also tells you the units, which is in atomic units cubed. So in this case, the volume is maybe 270 Bohr cubed for the simulation cell. And then you do that again for a set of volumes. So I prepared this here again in the morning just to keep, not to spend tons of time on this, because we do want to talk briefly about band structure. And so I gathered a bunch of volumes here by changing this lattice parameter, and I tabulated the corresponding total energy alongside those volumes that come out of your DFT simulation, and then I plotted it. Okay, so this is what the figure looks like. I'll switch back to my presentation here, like this. So this is our plot, which plots again the total energy in Rydberg, right? So Quantum Espresso gives you Rydberg versus volume. All right. And from this figure, you can now compute the curvature, right? You could look at the curvature of this figure. This is a little coarsely sampled, so maybe you want a couple more data points to sample this nicely. Then you fit a parabola to it. And from the parabola, you can then determine, the second derivative and use that to compute the Bott modulus. Okay, now we're in the remaining 8 minutes. I do want to talk about band structures real quick, because that's another nice example that you can use nanoHUB for. And then I can stay a little over time and answer questions if you guys like. In any case, the third example is if you're interested in, whether a material is a metal or a semiconductor, or if you know it's a semiconductor and you're interested in the band gap, for those kind of questions, you would try to simulate an electronic band structure. And I just put in a reminder here in case you've never seen a band structure, because again, we have a diverse audience. I just want to mention what is it that we're plotting when we're plotting a band structure. And so typically I like to show this for the free electron gas, because that's a model that you most likely have seen in some course, maybe your quantum mechanics or solid state physics course. And we're just going to do that in one dimension, right? We have a one-dimensional periodic lattice, and without any potential, right? So we just have kinetic energy. So that gives us this expression for the kinetic, or for the total energy, right? It's simply h bar squared k squared over 2m. K is your wave number in reciprocal space. And that is something that you can plot. Okay, so we take this, I'll do this maybe in red. I plot the parabola that comes from this relation. Okay, so this is what this parabola looks like, just the parabola and k. Now, because the material is periodic, or the lattice, in this case, the one-dimensional lattice is periodic, we have Bloch's theorem. And what that tells us is that we can do one of two things. We can either plot a bunch of these parabolas, right, that go through entire k-space, or alternatively, and that's what we're doing in our simulations now, we restrict ourselves to the first Brion zone. Because the material is periodic, the reciprocal space is periodic, and the Brion zone, your first Brion zone, is the unit of periodicity. So if you know the information in the first Brion zone, you know all the information there is. Okay, so that's what we're plotting here, right? The reminder, I think it's labeled in this case, we plotted the total energy, which is this one, as a function of k. Maybe I'll label k here real quick. So this is your k-axis, which is this k. This is what a band structure is. So we have plots that look like this in your first Brion zone, right? You have all these bands. The lowest one comes from within the Brion zone. The next thing here comes from the two adjacent Brion zones, and so on, right? So you get all these bands in your plot. But that's what a band structure is. It's just the energy as a function of k. All right, so that's one dimensions and free electron gas, right? So no potential. This gets a little bit more complicated if we go to 2 dimensions. We are still using free electron gas for now, but we go to 2 dimensions. Okay, so what happens in 2 dimension is your Brillouin zone becomes 2-dimensional, right? So now it's not a 1-dimensional Brillouin zone anymore, it's a 2-dimensional Brillouin zone. So in this, let's say we have a square lattice, cartoon picture of the Brillouin zone is this, first Brillouin zone. Now you have 2 k-axes, right? You have kx and ky. And the information that you would have to visualize is now, so in 1 dimension, you can simply visualize everything, right? In 2 dimensions, well, you have k-states everywhere here, right? These k-states are discretized with the spacing that scales with the dimension of your crystal, right? With the overall macroscopic dimension of your crystal. So the spacing is pi over L. So in other words, you have a large number of k-states here. That's a large amount of data already, and visualizing that is tricky. And so what you do is, again, if you've seen a band structure, this is nothing new. But if you've not seen a band structure, maybe it is new. So what you do is you pick paths along high symmetry lines through your Brillouin zone and plot the data along those paths, right? Instead of plotting it for the entire Brillouin zone, you're just picking high symmetry paths and plot the data along those paths. And actually, I want to use different colors, which is why I'm erasing this real quick here. And then you use these paths as your x-axis, and you plot the energy as you go along those paths in k-space. All right, so let's start with the red one, gamma to x. It's this one. So you start at the gamma point, you walk over to the x point. You start at the gamma point, you walk over to the x point. And as you walk through k-space, you compute this function and you plot it. This is what the band structure looks like. And you can do that for other directions, right? So gamma m I made green. So let's do green. Would be the next one. It's gamma m. And then mx is blue in my plot. Okay, so I'm going to make this blue here. All right. So you go through these high symmetry lines in k-space and you plot your energy as you go through those lines. It's up to you which lines you pick. It's up to you how many you pick, but the resulting plot depends on that. Okay, so this is where this plot comes from. Now in 3 dimensions, it gets a bit more complicated because now we have a 3-dimensional Brillouin zone, which is shown here schematically. This is for, again, I believe for a cubic lattice, what I visualized here. I took this, by the way, from the Bilbao crystallographic server. They have very nice illustrations of these Brillouin zones. Anyway, so you have a 3-dimensional Brillouin zone. That means our path along high symmetry lines that we pick is now in 3 dimensions, right? Those lines go through 3 dimensions. But the idea is the same. We use those paths, use it as an x-axis, and plot our energy as we march through our 3-dimensional Brillouin zone. Okay, the reason I put schematic here is because this band structure is now not a free electron model anymore. Because, of course, in a real material, we don't have a free electron gas. In a real material, we usually have electron-ion interaction, right? So the ions do cause a potential for the electrons. We have to take that into account. And so in a real material, you get things like gaps here, you get a gap here. So this is, for instance, I believe this is for magnesium oxide. In any case, there are 2 things that happen. Number 1, our path through k-space is 3-dimensional. And number 2, we get gaps here, which you didn't see in this case, because over here we had free electron model, over here we have real material with electron-ion interaction. So that's a band structure. And in the last 2 minutes, I'll show you how to compute that with nanoHUB, with Quantum Espresso again. And so I would suggest, if you're following along or if you want to try it out later, restart your tool and start from the input window again. And then we do 2 things. We use a couple of data points to sample our band structure. So that tells you essentially how many discretizations do you want in between 2 high symmetry K points. So you can use 15 to 20 if you want the band structure to look somewhat smooth. And then you pick high symmetry points. Right? So you choose, you decide. It's up to you. Whatever you want the path to be, you have to decide that. But you have to pick some, and I think I picked those 3 here for this demonstration. And then you hit compute, and we're going to get a band structure and a density of states. Okay, so let me show you what that looks like. So I think I can, in my case, already just, let me go back to the input actually. So you go to the band structure simulation here. This is where you put your high symmetry K points in, your list of high symmetry K points that you want to capture in your simulation, right? So the path that you want to walk along in the on the x-axis of your plot. So in this case, you start at this point, 0.5, 0.5, 0.5. You go to the gamma point, which is 0, 0, 0, and then you go, I think, here to the x point. How to know what to put here? This is something I usually take from the Bilbao crystallographic server that tells you that tells you the coordinates of these high symmetry K points. But in principle, that's up to you. And then you can tell how many points you want to have in total here to discretize your simulation. And then you just hit simulate. I'll do that real quick. Sorry, here we go. And then in your output, again, minus fast because of caching, you have two pieces of information. One is your electronic band structure plot, and one is your density of states plot. And so I'll show you that real quick in my presentation. I just have to jump back to that one more time. So what these figures now show is on the y-axis, the electronic energy, on the x-axis, your k-point label. You can see that this code or the nanoHUB website does not label it with high symmetry coordinates. That's something you have to do. But we ran from this 0.5, 0.5, 0.5 to the gamma point, all the way to the x point. And then you see bands here, right? You can see all these different bands, all your electronic states in silicon. The dashed line indicates the Fermi level. So you have some empty states and you have some occupied states here. And then at the same time, the code also uses that information to produce a density of states, right? So you sum over all the k points, making this function simply energy dependent. And then you count how many states exist in a certain energy region. You can plot that again. Fermi level is the dashed line. For teaching, this is super instructive because having students pick their own Brion zone path, I think this is key for people to understand what's going on in this band structure plot. The first time I saw this plot, I was highly puzzled, and doing it yourself really helps. And I think nanoHUB is a great tool to do so. So we have them illustrate the path in the Brion zone, right? They should pull a picture of the Brion zone and draw their path in that Brion zone. Then they put it into nanoHUB. They can look at direct and indirect gaps in the material, right? Silicon is very conducive for that. You can also explain the mapping between band structure and density of states, right? By aligning these two plots, you can rotate the density of states plots and make it such that the states align with the bands, and that helps students understand that concept. And you can also have them extract effective masses. I'm not doing this in this webinar today, but these are things that we do in course projects, for instance. All right, so at this point, I'll stop here. We're out of time for one, and second, I think it was a lot of information already. So what I want to say on my conclusion slide, I put a couple of books here. So DFT is well established. You find very nice books. Personally, I learned it from this book in the beginning by Dreitzel and Gross. It's a bit more physics heavy and maybe math heavy. If you're more interested in implementation, I would say Richard Martin's book or David Scholl's book are great books. By no means is this list exhaustive, right? You will find, if I'm not citing your book and you're in the audience, I apologize. There are very many pieces of literature out there that are excellent and that you can also refer to. These are simply books that I have experience with that I used. If you want to go to better descriptions of these electronic states, you will find very quickly DFT is actually not suitable for that. And we have to go beyond DFT. That's probably the topic. It should be the topic of another webinar, but if you're interested in excited electronic states, I put a couple of references here. Again, these are books. The literature papers and review papers is, of course, even more exhaustive. I want to highlight two things. Number one is, so I'll do Q&A after this, but Amy and Tanya created a DFT group on nanoHUB that you can join and post your questions there. So if you want to do that, feel free to do so. We'll try to answer those questions after the fact and maybe offline. You can reach me here if you want to. And the last thing I want to reiterate is that we do have a survey. There will be a survey that Amy sends out. Please take a moment and fill out that survey if you liked or disliked this webinar, because this feedback is taken seriously and we can use it to improve future webinars, for instance, and also account for topics that you're interested in. Anyway, at this point, I'll stop and I'll thank you guys for your attention. If you have any questions, please feel free to post them. Thank you.
All right, great. Thanks, Dr. Schleife. The first question. Exchange can be corrected from the self-interaction error using several strategies. Which do you recommend, Hubbard, hybrid functionals, or meta GGA?
That's an excellent question. I don't think I'm an expert to recommend specifics here. I would say it depends on various things. Number one is computational cost. So these three approaches that you mentioned come with different computational costs, right? So hybrid functionals can be more expensive. GGAs and meta GGAs may be a bit more cheap. It also depends on the basis that you're using, how expensive these functionals exactly are. So that cost is number one. You have to kind of keep that in mind. Number two is the physics is very different in those approaches, right? So for instance, when you do a Hubbard U, you typically have to either know or somehow obtain a U value that you impose, and that may be well or not so well justified. So it depending on what exactly you do, that can be either a benefit or a detriment. And then it depends also on what you want to compute from it. So let's say if you want to compute excited state properties, some of these functionals may be better suited to that than others, right? So let's say you want to compute a band structure. Normally, what we'd have to do is something like these excited state methods, like for instance, many body perturbation theory, but that includes a certain amount of exact exchange. And so maybe a hybrid functional in some ways does that, and that could be a way to go. But again, I think it depends very much on the specific simulation that you have in mind, which strategy to recommend.
All right, great, thanks. The next question, can DFT be used for dielectric simulations?
So generally speaking, yes. It depends a little bit on what you mean by dielectric. And I don't want to be evasive, but there's at least the electronic dielectric properties and the lattice dielectric properties. For both, you can use DFT, right? So the electronic dielectric properties would come from essentially a band structure or simulation, and then computing the dielectric tensor from that. And DFT can be used for that, absolutely. And it comes with, accuracy limitations, just like any of the excited electronic simulations. And then if you're more interested in the lattice dielectric properties, approaches like density functional perturbation theory are used, which build on DFT, and they can compute, lattice dielectric properties. So those dielectric tensors and things like that. So those things exist, and you can use them for that. Now, how accurate those simulations are, again, I think that depends a bit on the material system and what exactly you're looking for. But generally speaking, I would say the answer is yes, with the caveat that we may have to look at the accuracy as a bit of a detail.
The next question, what is the significance of K points?
The significance of K points. Well, okay, so let's say if you want to solve a differential equation, and we start with the Quantum equations in real space. One way to do that is you discretize real space and you solve your Quantum equation in real space. So you can do that, right? That would be a real space solution, and there are codes that do exactly that. Alternatively, if you have a periodic system, you want to exploit periodicity and you want to exploit Bloch's theorem. And so what you do is you sort of like exploit this periodicity by Fourier transforming your differential equation. So differential equation here being the Quantum equations. You Fourier transform it into K-space and you use periodicity explicitly. And so the meaning of K points, I would say, is it's the Fourier transform of real space, and then we are now looking at our system in reciprocal space. So it's the Fourier transform. But then once you're in K-space, you're still at the same you still have the same problem, which is you have to sample then K-space, right? So that sampling problem does not go away. But I think the reason we're using K-space here is the fact that the systems that I talked about today are mostly periodic. And so we exploit periodicity by operating in reciprocal space. If you're looking at molecules, let's say, or atoms, for instance, you can absolutely stay in real space and not deal with K points. So maybe that's where I'll leave it at.
All right, thanks. The next question, are there well-known materials for which simulations using these techniques are extremely inaccurate?
So yes, well, that's a good question. I mean, known groups of materials, I don't think I'm the right person to necessarily answer that, but one thing is challenging, and that is a correct description of the electron-electron interaction. And so sometimes people cite that materials that have very strong correlation effects as challenging. However, that is, I would say, a somewhat diffusely defined group of materials, meaning if you tell me a stoichiometric formula, I cannot tell you upfront, is this a strongly correlated material or not? And so we'd have to then look at the details. And on top of it, there are recent directions in literature that investigate disorder as the reason that sometimes can account for some of the disagreements that were previously attributed to a strong correlation. So I think that's not such an easy question to answer. But generally speaking, I would say metallic systems are typically, again, this is a risky statement to make, but metallic systems are typically better described with something like a local density approximation. You will always find exceptions, and you will always find properties that don't work well, but usually a local density approximation works a little bit better for simple metals. If you start having d electrons and f electrons and things like that, then errors like the self-interaction error starts to hit more severely and you have to fix it. So in other words, there are all sort of things that can go wrong, and it depends very much on the specific system. But like I said, be careful with d and f electrons, maybe be careful with van der Waals interactions, things like that. But again, that's not the exhaustive list. I realize that.
can we calculate electrical and thermal conductivity using quantum espresso?
So I have not done this myself directly, but I believe so. Yeah, okay. Generally speaking, yes. Meaning you would probably would start with Quantum Espresso and then use tools that build on it. So the electrical conductivity, you could start maybe from a band structure description and look at mobility and effective masses and things like that. Thermal, but then you want to also account for phonon scattering and things like that. And there are codes that do that. They take into account, for instance, the lattice response and stuff like that, electron-phonon interaction. I think the code I would probably point you to, without ever having used that code myself, but the code that I see in the literature being used for that is maybe Boolt's-trap. So this solves Boltzmann like equations to get at those kind of conductivities. The idea there is usually you would use DFT output to parameterize a model that gives you something like a conductivity and things like that. But in principle, Quantum Espresso is very versatile and it can be interfaced with these kind of tools. Again, I'm not a Quantum Espresso expert, but I think you have a good chance to at least get started with that, yes.
All right, the next question, could you please explain the energy cutoff in the input file?
Yes, the energy cutoff. So what you do is, think of a Fourier transform. If you have a function, let's say a sine wave, that you want to represent in a Fourier representation. Okay, so what you do is typically, if you've ever done a Fourier expansion, you start with a certain frequency, you go to higher and higher and higher and higher frequencies, and that as you go along, as you include more and more frequencies in your expansion, the description of your expanded wave function or wave function in our case gets more accurate relative to the actual exact real wave function. So it's really a basis set expansion. And now, in case of plane waves as a basis set, this is actually very close to a Fourier transform. So we use plane waves of increasing frequency in our expansion, and the cutoff tells you up to what frequency your basis is taken into account, right? So you start with 0, and then you go, to higher and higher and higher frequency or energy, and at some point you cut off and you ignore all the higher energies in your basis set expansion, and that's what this cutoff determines. The cutoff determines the kinetic energy of the plane wave that is the highest one that's included in your expansion.
All right, great. And I will ask one last question. Can we use DFT for nanomaterials?
Yes, in principle. So there is no restriction from a materials point of view. There is a practical restriction, which is depending on what exact DFT code and DFT flavor you use, you can only study up to a certain number of atoms. So that's not a hard cutoff in any way, but it depends on the size of computer that you have available and things like that. So in other words, the more atoms you include, or really the more electrons you include, the more complicated your simulation will be. And that means in practice, the more computational resources you need. And so depending on what you mean by nanomaterial, that could be the problem there, right? So let's say if you want to do a nanocrystal or a nanorod that has 300 atoms, you can definitely do that in DFT. If you want to do a nanocrystal that has 1 million atoms, you most likely cannot do that in DFT. So don't quote me on the million. I didn't follow the most recent developments in these linear scaling methods and things like that. But usually the more atoms you have in your simulation, the more difficult those simulations are. And that may be a practical limitation from that point of view. But there is no fundamental reason other than computational cost that limits you in using DFT for a nanomaterial. If you have a large number of atoms, you may want to look at other approaches, but that is really the only limitation that I would think is an issue here.
All right, great. Well, thank you again, Dr. Schleife, for this great presentation. Thank you everyone for attending today and asking all the great questions. And with that, I think we'll go ahead and end the webinar.
Okay, thank you guys for attending. Thanks.